In this video, we're going to examine what thermal noise looks like and how we describe it. Thermal noise consists of random vibrations of electrons in a resistor, and so that means the total current in a resistor is going to be given by some amount of deterministic current flowing in the resistor, which might be 0, plus a random amount of current that is normally distributed, which is to say that it's a Gaussian. We say the noise is Gaussian because it's the sum of many independent random processes. Each electron in the resistor is kind of deciding whether it's going to run left or right in a given time differential. And the sum of lots of random processes converges to a Gaussian by the central limit theorem. This Gaussian has some standard deviation, which we call sigma I, and that standard deviation is a measure of how strong the noise is. We call that the noise current. We could measure this Gaussian by looking at a resistor for a long time and making a histogram of all the currents that we observe in it, which would be called the ensemble distribution of the noise in the resistor. But that ensemble distribution doesn't represent the noise at any particular time. A property called ergodicity, which we're not going to be digging into, means that the distribution at each unit of time happens to match the happens to match the ensemble distribution. This device is still a resistor, so the current and the voltage are linearly related. That means the noise voltage is also a Gaussian, but the standard deviation is R times bigger than the noise current, which, as a reminder, is the standard deviation of the current. Also, as a quick reminder, the standard deviation of a distribution is the same thing as the root mean square value of a distribution. That's good to keep in mind because there are lots of notations for noise, some of which represent RMS voltages instead of standard deviations. We're going to pull a few results from statistical mechanics with little justification on the rest of this slide. Statistical mechanics says that the variance of power is equal to Boltzmann's constant, K, times the temperature. And that's true in each differential bin of frequency. I've represented that with an equation at the top of this column and with a picture in the middle. This statement says that there's some noise energy at every frequency, which is why this type of noise is often called white noise. And that's because white light has some energy at every frequency, so this is kind of making an analogy there. That analogy gets extended sometimes. Noise that has its energy clustered at low frequencies is often called pink noise. Alright, so this frequency domain picture is kind of alien to us, right? It's like we're saying there's some amount of energy at every frequency, and that's how we represent our noise. In the time domain, what that means is at every instant, there's going to be some little Gaussian superimposed on top of our signal, which I've tried to indicate by drawing this centipede here, and that those Gaussians are uncorrelated from each other. So knowing the noise on top of your signal at one instant doesn't tell you anything about the noise on top of your signal at the next instant. It's going to be pulled from the same Gaussian distribution with no relationship to the prior value. Finally, a different bit of statistical mechanics tells us how this noise power turns into noise voltage and current variances. This is the amplitude of the voltage or the current fluctuations on a noisy resistor that would explain the total noise power it emits. So these equations let us calculate the standard deviation that we see in our noise voltage or current. We've introduced a lot of different measurements of noise, and it's worth comparing them. The first column here has the name of quantities, and the second has a symbol we're going to use for them. The third explains whether the quantity is a standard deviation or a variance, and also whether they're total values or densities. A density in this situation refers to a quantity that appears at every value of frequency, so like the KT we saw in the last slide was a noise power density. And we can identify whether an equation is a density by looking at where the delta F appears in our equation. In general, if something's multiplied by delta F, it's a total value. If it's not, it's probably a density. We'll explore how to find the value of delta F over the next two videos, but I don't want to get too deep into it right now. I just wanted to call out the difference between a density and a total value. Total values are things that you observe in your circuit. Densities are some sort of mathematical idea about how noise power is spread out over multiple frequencies. The fourth column here just gives an algebraic expression for each of these quantities for a resistor. And they're often pretty straightforward manipulations relative to one another. So I invite you to go through and derive where each of those equations came from. Finally, the last column gives the units of each of these noise quantities. There's a lot to call out here. However, I'm going to confine myself to a few notations. First, noise voltage variance density, or sometimes noise power density, depending on what type of calculation you're doing, is called spot noise. Spot noise refers to the white noise level in a problem. So on the previous slide, we would have said KT is our noise power density spot noise. Right, it's just the level of a distribution. Noise voltage density is denoted in volts per root hertz, which is a very strange unit. The square root of hertz doesn't show up a whole lot in sort of day-to-day use. That's a byproduct of the fact that that noise is much more natural to think about in terms of variances than standard deviations. So you wind up with this weird, quirky square root of hertz unit because you're insisting on using a standard deviation where a variance would make more sense. And finally, I've introduced one more noise metric on this slide that we didn't talk about on the last slide, which is in the last row. That's called a noise temperature. Noise temperature is just a different way of representing a noise power density. It's the temperature that would produce an observed noise power density. So if you observe some amount of noise power, noise temperature is the temperature that would result in that in a normal resistor. Thus far we've only seen noise generators that consist of single resistors, so our noise temperature is always equal to the physical temperature, T. But as we start looking at more complicated circuits, noise temperature is going to be a really useful shorthand for how noisy something is. So, in summary, thermal noise is white and Gaussian in both voltage and current, and I've given expressions for the variance of noise voltage and noise current here. Thermal noise implies a power density, so the noise power is equal to KT times delta F. And noise temperature is the temperature that would explain an observed noise power level. So that's just a rearrangement of the equation in the middle of the slide to express noise power in terms of noise temperature.